speaker is Charles Gia, Department of Chemical Engineering and Applied Chemistry, University of Toronto, and we're going to try to conserve lateness, so you'll have the full 20 minutes, and I will give you 3 when you have 3 minutes and 1 when you have 1. Okay, thank you. Yep.
Okay, good morning, everyone. Thanks, Scott. I'm Charles Gia from University of Toronto. I actually drove the day ago from Toronto about 900 kilometers, not very far. Okay. So my talk is also related to biomass, but in this case, that is a biocarbon. Okay, biocarbon basically that is carbon from biomass. Simple. Okay. So before I start to talk about biocarbon, I would like to acknowledge the people contribute to our work on biocarbon. Evan actually is a visiting PhD student from Sichuan University in China. Randy is a PhD student. Jonathan is graduated last year, also PhD. Benedict is a visiting student from Germany. And Aldridge is a master's student, and my colleague and my good friend, Donna Kirk, is an electrochemist. So let's talk about the important thing first, just in case Scott cut me off. Okay. So the key message here is that a large-scale production and utilization of a biocarbon could represent a viable means of capturing, storing carbon, and the biocarbon itself can become part of a tool set to reverse climate change. Okay. So basically, I'm going to argue this point based on 3 elements. So first of all, I'm going to talk about briefly global carbon cycle. Later on, I'm going to explain what is pyrolysis, which basically converts biomass to biocarbon. And lastly, I'm going to give you an example of how we use biocarbon. In this case, we're talking about energy storage in a device called supercapacitor. So this is actually a relatively old, actually, mass balance of carbon for the entire Earth. Okay? So if you look at those numbers, there are red ones, blue ones. Okay? Blue ones are actually an amount. Okay? If you look at the corner here, the atmosphere 750. The units actually is gigatons or billion tons. So we are talking about 750 gigatons of carbon, mainly as carbon dioxide in atmosphere. Okay? In other words, that roughly every people on the Earth have 100 tons of those carbon as carbon dioxide in atmosphere. Okay? So another numbers, other red number actually is fluxes. I want you to pay attention to this number. Okay? The 6 here is basically the total amount of carbon emitted as carbon dioxide as a result of using fossil fuel. This number probably now should be roughly close to 8. Okay? So another number I want you to pay attention to is this 120. This is actually amount of carbon absorbed from the atmosphere by photosynthesis. Okay, so 120. That's 120 gigatons per year. It's a huge number. Okay, so another number I want you to pay attention to actually is soil respiration and also litter flow. Okay, this actually is, say, for example, the tree leaf falling on the land, then due to activity of a microbe. Okay, those leaf will become, say, send back carbon dioxide, and water becomes goes sent back to atmosphere. So the point I want to make here is that the net removal of carbon, okay, by photosynthesis is about 60. Okay, so the point I want to make here is that if we can cut this 60 by reducing amount of carbon released back to atmosphere, then basically that we can reduce amount of emission from land to the atmosphere. Okay? So this is actually why we are here. This, of course, is an imbalance, imbalance of input or output of carbon dioxide from land. So in order to solve this problem, we are looking at many ways. For example, that people are looking at increased energy efficiencies, developing renewables, including biofuels. Then we are talking about reinvesting in nuclear powers. We have carbon capture storage, and also we're talking about artificial leaves, and also we're talking about artificial beef change behavior of our habit. Okay. So what I'm talking about here is that how about biocarbon production and utilization? That as another way to solve the carbon dioxide challenge. So here is actually a biocarbon. Okay? So basically, biocarbon is a biochar. Most of the people use that term. But in our case, we define biocarbon as biochar with high carbon content, over 98%. So how can we actually use biocarbon to reduce carbon dioxide emission? So the key process here is pyrolysis. The pyrolysis actually is a process which actually converts biomass or extract biomass, carbon in biomass. Okay? So for example, that if you look at outside, okay, the tree, grass, dry tree and dry grass contain 50% of carbon, okay, in different type of forms. And the pyrolysis process actually can extract those carbons. It's a high temperature process. Okay? So the biocarbon produced from pyrolysis, depending on the raw materials, what type of biomass you use, also depending on the temperatures, heating rate, the pyrolysis conditions. And if you have an extremely high temperature, those biocarbon can be graphitized and becomes very electrically conductive. Okay? So in our lab, actually, we use wood as raw materials for producing biocarbon. The reason for that is because of the structure of wood in different part of wood. So this is actually biocarbon produced from maple wood. You can see that the structure in wood, the macrostructure in wood, has been retained. We believe that this type of structures is beneficial for mass transport if we are using this type of carbon for electrodes in supercapacitor. This is actually softwood. It's a pine. If you pay attention to those small scale here, this is called pit. Okay? We can actually control the process condition that we can close and open this pit so that to improve mass transport of, say, ions in electrolyte in case of electro applications. The bottom line here, I want to mention here that if we treat these wood materials carefully, we can retain or control the structure in wood. So everybody knows about carbon allotropes of different type. And this is actually the structure, the picture we took from biocarbon from maple. What you can see here is that we have graphite nanocrystals in those biocarbon. Okay? This is treated at high temperature. So this is actually the property of different type of carbon allotropes. So ideally that in order for us to have high electrical conductivity, we want to produce graphite or graphene type of structure in biocarbon. We also measure the porous structure of biocarbon as well. But you can see here that is actually the left panel is pore size distribution. So we are talking about micropores, so sub-nanopores of a different type of wood. And on the right-hand side, we're talking about the crystal size of those nanographite crystals. What you can see here is that we have different size of those crystals produced under the same condition, but from different raw materials. As I mentioned several times, that the conductivity actually is one of the properties we pay attention to because it's one of the key properties for materials, electron materials. So we look at the properties, conductivities of biocarbon derived from different wood. So what you can see here is that there's strong correlation with carbon content of the biocarbon, which is not so surprising. One important thing here is that if you compare the highest, say, the conductivity is over 25,000 Siemens per meter, compared to actually about 300 Siemens per meter if it of graphite perpendicular to the basal plane. So we have talked about the biocarbon. Basically is that carbon derived from biomass and some structural properties, conductivities. The typical application of biocarbon is well known for as soil amendment and also for water, air purifications. There's some research on, say, for as an additive to construction materials, even as a sensor for detecting trace level of heavy metals, and as a catalyst, there's some newer studies, a catalyst for hydrogen production from waters or carbon dioxide reduction, but those are very micro applications. Again, as example, I'm going to explain that in our work that electron materials for energy storage in supercapacitor. So one of the things people realize that the high efficiency energy storage is a central issue for renewable energy. This is actually Tesla's lithium battery bank in Australia. Okay? It's 100 megawatt power, okay, in Australia. So there's a need for developing this type of stationary grid level energy storage device. So we are thinking that if we can use supercapacitor instead of battery for that purpose. So this is actually well-known diagram talking about difference between supercapacitor and battery. Okay? So both are energy storage device for storing electrons. The supercapacitor is a physical device and the battery is a chemical device. Supercapacitor tend to have a higher power density but have a lower energy density, okay, compared to battery. So you can charge supercapacitor very fast, but cannot store so much energy in supercapacitor compared to battery. Okay? Here is actually Tesla. Okay? It's powered by lithium battery, the old generation of lithium battery. Okay? You charge it for overnight. You can drive it for perhaps say 200 miles. Here is a bus powered by supercapacitor. Okay? This is actually about 9 years ago in Shanghai. You have to charge it every 500 meters, okay, every stop, but you charge it within seconds when you load, upload, okay, passengers. So the reason for that is very much because of supercapacitor have a low energy density, but can be charged in a very short period of time. So how can we increase actually energy density of a supercapacitor? Okay? So there are several ways you can do that. One way is to actually increase volume fraction of active materials in the device. I will explain that later, okay? Another thing is that increase actually capacitance of electromaterials. In this case, that is capital C, okay? The E here is energy. If you look at that equation, the energy stored is proportional to the C. Okay, if you increase C, then you increase energy. Okay? The C, again, is proportional to the useful specific surface area. Okay? The C also can be increased by introducing pseudocapacitance by induced chemical redox reactions. So in that case, our supercapacitor can have two types. Okay? One type is called double layer, which is purely surface phenomena, no pseudocapacitance. Okay? Another one is pseudocapacitors. Okay? They combine this as a hybrid capacitor. So hybrid capacitor is, in principle, that is a physical plus chemical device. So what type of materials is best for as a supercapacitor electrodes? First of all, you should have a high specific surface area. Second, that should be conductive. The conductive in two sense, okay? One is conductive in terms of electrons, another one is conductive in ions, in electrolyte, in supercapacitor. Of course, should be cost-effective, environmentally friendly process to produce it, okay? So if we're talking about first two, the nanotube, okay, may be the best choice, okay? But on the other hand, the nanotube, we know that's not cheap at all, okay? So what we are thinking here is that how about we use monolithic biocarbon as capacitor electrodes, okay? So on the left side actually is a configuration of a commercial supercapacitor electrode. You have a thin film structure, okay? The reason for that is because the thin film is made of active carbon powder, binder, okay? The binder tend to be organic materials, non-conductive. As a result of that, those materials highly resistive, electronically resistive, so that you cannot actually produce thick electrodes. So as a result of that, the volume fraction of materials in the electrodes are actually very low, okay? So in this case that we test the idea that if we can use the thick electrodes to replace those thin film, okay? As thick as 10 millimeters. Usually that the commercial one is about 50 microns. So actually our test is quite, we shall say, quite successful, okay? This is a comparison of commercial, say, cell, okay? Both are 100 farad, okay? So if you look at mass, the commercial cell is about 23 grams and energy density of 4.6, and our cell with both electrodes and 2.8 grams, and energy density is higher, and dimension is slightly smaller as well, okay? So we also test our cells actually under different conditions with different electrolyte, okay? What we found is that, yes, our cell actually have a much higher power density than battery, which is expected, okay? And, but still, the energy density is lower than the battery, okay? So we, in order to increase energy density, we modify these carbons with ruthenium oxide. This is actually result. What you can see here is that the black one is untreated, and the color ones are treated ones. You can see that there is an increase of almost 4 times. Okay? And also we tested the electrode stabilities and say up to 1,000 cycles, very stable performance. Okay? And also we compared the energy density with literature values. This is actually also 1 millimeter thick electrodes. Ours is 1.2 millimeter thick electrodes. Okay, so again, the key message here is that, okay, large-scale production and the utilization of biocarbon could represent a viable means of capturing stored carbons. The biocarbon can become part of the tool set to reverse climate change. Thank you very much.
Thank you very much. Okay, open for some questions, please. Thank you.
What fraction of the world's projected energy storage needs do you think could be fulfilled with supercapacitors?
I think supercapacitors, the storage is ideally for renewables, okay? For the wind and solars, okay? So if you're talking fractions, I think based on the US Energy Information Agencies, if you were talking about 2014, maybe at that time, 15% is renewables, okay? So I would say that probably that will be the amount of fraction of energy ideally for this type of device.
Yes, please.
Yes.
Okay, there are many research on the graphene usage for the supercapacitor. And can compare the biocarbon with graphene, which is better for the supercapacitor?
Yeah, I think the graphene is, if you're talking graphene, it's very much the same group of nanotube, right? So sp2 type of carbon there, okay? If you're talking about performance, if you're talking about in thin film configurations, definitely graphene will be better than this carbon here. So the carbon or carbon here that contains nanoparticles of graphite, okay? And most important point I want to make here is that is the thickness of these electrodes, okay? The thickest, say, electrodes of a nanotube, I heard is about maybe 1 millimeters. In our case, we can increase to 10, even 15 millimeters thick. Okay, so yeah. So the performance is very much determined by configurations of electrodes. So it's actually difficult to, and also in terms of cost issues, it's very different.
Okay, so in the interest of time, let's thank Charles one more time, please. Thank you. I know that each of these talks is going to generate a lot more questions than we have time for, and that's why we have a coffee break.